Hello and welcome to the lecture on uh, Bayesian Parameter Estimation. So we have already seen the uh, MLE approach, maximum likelihood approach, estimation approach, or MLE, where we try to find out the parameter associated with the process. Just recall that we were doing a coin tossing experiment, and we were trying to compute the optimized parameter theta cap, and we got it as so the count on the heads, total number of heads appeared divided by the total number of tosses that we have done, right? So this represents heads, number of heads, and this represents the number of tails. So in the 5 coin toss experiment, so we have seen that we got 3 heads and 5 total tosses, and we computed it as 0.6, right? So this was MLE approach. Now let us assume that the coin was a fair coin, right? Assume assume that the coin used for the experiment is a fair coin. So just recall that while doing this experiment, I was just telling you that we don't know about the nature of the coin, right? But now I'm saying that what about if the coin was a fair coin? So would you agree with this result, right? So you will not readily agree with this because you have a prior notion of getting head is 0.5, or even getting tail is also 0.5, right? So you will not jump into a conclusion that this coin would be a fair coin, right? You will assume that it's a bent coin, right? But suppose that you done this experiment for let's say 10 lakh times, right? 10 lakh times we have done this experiment. So would you now again let's say we got 3 lakh times. 3 lakh times we got head. So again it is 0.3, 0.6 or 0.3, right? 0.3. So we have conducted the experiment enough number of times, and we have recorded the outcomes, and we got that this is around 3 lakhs. So would you agree with this statement, whether it is a fair coin or a bent coin, right? So the problem is the MLE approach in general does not allow to incorporate our prior knowledge, right? So we want to somehow incorporate our prior knowledge, because most of the times, as we have stated earlier in some lectures, we have very limited number of data that is available, or sometimes we may not be able to even conduct the experiment for several number of times, right? So in that case, we may have to try to incorporate the prior knowledge that is there if you are an expert into the model, right? So the Bayesian approach will permit you to incorporate your prior knowledge in the model, right? So the Bayesian statement is, so Bayes rule is, so in terms of the parameters and the data that we are discussing, so in terms of the parameter theta and the data, so parameter given data is proportional to probability of data given parameter theta multiplied by the prior, right? So this is the parameter, and this is the set of data, and this is posterior probability, and this is your likelihood function, and this is our prior. So Bayesian approach gives you a method to update the likelihood function with the prior knowledge. So this is very important. So in the case of MLE, maximum likelihood estimate, we were actually trying to compute this likelihood function, right? So our goal was, so given the data, right, or starting with the assuming the parameter, how likely this parameter associated with some process will generate this data. So that was our interest while computing the likelihood function, right? So now we have prior knowledge, and we can multiply this, or we can update the notion of the probability of likelihood with the prior knowledge, and we can compute the posterior probability. So that will incorporate your prior knowledge in the model, right? So the approach is basically, we have to have a joint distribution. So we create a joint distribution over the parameter theta and the observations. So what is our observation? Observation is basically theta. So x1 comma x2 up to xm. So these are nothing but the outcomes of the coin tosses, right? So we are trying to create a joint distribution And later we will convert this or represent this joint distribution in terms of conditionals, and we will try to compute the parameter theta, right? So so just make a note that in MLE approach we have assumed about the model. So the assumptions were assumptions in the case of MLE was the coin tosses were independent, right? So the coin tosses, outcome of coin tosses, were independent, right? And one more assumption was we have fixed the parameter theta as number of heads. So these were assumptions we made during the MLE computation, right? But if we don't know, right? If we do not know theta, then the tosses are not marginally independent. Right? So if we do not know the theta, then tosses are not marginally independent, and each toss tells us or tell us something about the parameter theta. And thereby about the probability of the next toss. So we are going to compute this. So if you don't know the theta, then the tosses are no more marginally independent, and each toss tells us something about the parameter theta, and thereby the probability of the next toss maybe we can compute from this, right? So but however, once theta is known, the controlling parameter theta is known, we cannot learn about the outcome of one toss from observing the results of others or other tosses, right? So thus we assume that the tosses are conditionally independent given theta. So these are the assumptions on the Bayesian approach, and we have contrasted it with the MLE approach, right? So now we can draw the model. So basically the plate notation. So this is our random variable, and the plate notation represents the repetition of the experiment. So m tosses. So this connected with the parameter theta, right? So this is so in on the let me just make a theta of x. So theta of x is basically you can see that so this is x1, x2 up to xm, m number of tosses we have, right? So this is our model. So let's start specifying the local probability models in the network. So we can write something like probability of x of m given theta as this is theta if x of m is by x1. So this is hertz, right? And 1 minus theta if x of m is x naught. This is tails, right? And the prior, so we have to incorporate the prior. So what is our prior? Prior is p of theta, and which is this is a continuous density over the interval right? So this is a continuous density function over interval 0 and 1. So let me write this probability of x1 of probability of x1 comma x2 comma up to xm comma theta. So we are expressing the joint probability distribution between the data, observed data, and the parameter theta, right? So this is our data and this is our parameter. So remember, when we try to express in terms of Bayesian networks, we start with a joint distribution, right? So this is the joint distribution of this problem. So this is basically what. So this I can write it as conditional distributions over the data x1, x2 up to xm given theta, right, divided by p. So this is nothing but p of x comma y is p of x given y given x, p of x, just the product rule, right? So so this will be p of theta, product of all the m's, p of xm given theta, right? So so what is this part? This part is basically the tosses are conditionally independent of theta, right? So we have used that information here. So that's why we write this as a product form, right? So all these coin tosses are independent given theta. So that information we are encoding here, so that we write it as a product form, right? Right. So this is our likelihood function, right? So this is nothing but our the likelihood function L of theta, right? So this is our this part is likelihood function, right? So we have computed this earlier. So this I can write it as p of theta. So what was computed earlier? So this is 1 minus theta of m0, right? So number of heads we obtained, and probability of heads, and this is probability of tails to the total number of heads minus the tails, right? So now we can the posterior distribution of our posterior distribution over theta can be written as how? Maybe I can. So p of theta given data. So data is x1, x2, up to xm, right? Equal to what? Probability of data given theta given theta, then p of theta divided by the marginal distribution of the data, right? This is our Bayes theorem, nothing but Bayes theorem. XM, right? So this becomes the normalization factor, right? So normalization. Right? So this becomes a proper probability distribution. So that's why we normalize it. Right? Now we have to have some assumption on the prior, right? So if the prior is a uniform distribution, see, there are many priors or probability density functions you can take as priors. One of the simplest assumption is a uniform distribution. That means the probability of getting a tail or head, you are assuming that it's uniformly distributed, right? So this is the meaning of uniform distribution. So P of theta is 1 for all theta belonging to 0, 1, right? So this is the meaning by stating the prior is a uniform distribution. So if the prior is a uniform distribution, then the posterior is just the normalized likelihood function. Right? So there is a connection of posterior and likelihood and prior, right? So if the form of posterior, right, form of posterior and the form of the prior has something to do with the form of likelihood, right? So if we have a uniform prior, then posterior will be nothing but just your likelihood function, just a normalized likelihood function, okay? So there is a connection between the shape of posterior and the prior that maybe determines what form of the likelihood should be taken, right? You cannot just multiply these two and get the form of posterior for all kinds of distributions. There are some particular kind of type of priors you can choose to determine the form of the posterior, right? So so in this case we are assuming prior is a uniform prior, so that the shape of the posterior will be also similar to the likelihood function, right? So this is the meaning of saying posterior is just the normalized likelihood function if prior is a uniform distribution, right? So now we have to make some predictions. So let us try to predict. So we have to predict the theta, right? So like in the case of MLE approach, what we have done was we have computed the optimized parameter theta as theta cap, and we found that it is nothing but the average value, right? So in this case, so in this Bayesian approach, what could be the theta, right, or optimized theta? So and again we stated that we can make some predictions on the next outcome, right? So let's see how we can do that. So let x m plus 1, right, represents the value of next coin toss. So this is the thing we want to predict, right? So next coin toss of our plate model or the toss of the network. Right? So remember, we have generated the network as something like this, right? So we are going to see the next one, x m plus 1. Right? We are going to predict that. Okay. So we can compute the probability over the next m plus 1 given the observations of the first m tosses, right? M tosses, and note that in this model the theta is unknown, and we are considering all of its possible values, right? So in the case of MLE approach, we fixed theta as number of heads, right? But in this case, this is unknown, and we are actually trying to consider all of its possible values. So possible values are basically in the range of 0 and 1, right? So this is the difference between the MLE approach and this Bayesian approach, right? So there in MLE approach we were actually considering a single value for theta, right? Just an average, right? So let me express this mathematically. So probability of x, the next toss, given all the previous tosses, will be equal to, so basically we have to, because we are taking all the range from 0 to 1, we have to use an integral symbol, because this is not a discrete value, it's a continuous value. Theta is a continuous value from 0 to 1. So this is x plus 1 m plus 1 given theta, and the data is basically x1 comma x2 up to xm, right, multiplied by P of theta given the data x1 up to xm d theta, right? So we can write this as because this is a conditional probability distribution. We can write it as P of x m plus 1 given theta, because we assume that the given theta, right? You just remember earlier we have made a statement that if theta is known, right, it is independent of the number of tosses. So I can write this, so conditionally independent, right? This is conditionally independent. So this probability of some factor given something comma something, and this is independent, then you can avoid this, right? So that is why I have written like that. And then P of theta given to data x1 up to xm d theta, right? So we are integrating our all over theta. So we are going to integrate the posterior over theta to predict the probability of heads for next toss. So let me write this as a statement. So we are integrating over posterior integrating the posterior over theta to predict the probability of heads for the next toss. Right? So let me do this. So our prior was uniform prior, right? So the prior was assuming uniform prior theta over the interval 0 to 1. So this we have made already made the statement. So then P of theta given x1 up to xm is proportional to the likelihood, right? Is proportional to likelihood. So likelihood is P of theta given theta, right? xm given theta. Okay. So we have already computed this as theta of number of heads multiplied by 1 into 1 minus theta of 0. Okay. So we can use this in the above equation. So we are going to use this. So use this into the above integral. you want to see the integral, so this one, right? So so let me do that. So we can compute P of x the next toss as head given the data values x m is equal to so we have to write the normalization factor here. So normalization factor is nothing but the marginal distribution of the data. So that is nothing but P of some integral of the posterior the prior probability P of theta multiplied by so we are plugging that result of likelihood function that we have computed earlier, minus m of 0. So this is nothing but the likelihood function, right, multiplied by the prior, theta is the prior, and we are integrating all the possible values of the theta in the range of 0 to 1, right, and multiplied by a normalizing factor. So this becomes the normalization. So this is nothing but the Bayes theorem, right? So Bayes theorem. So now basically we have updated the likelihood function by multiplying the prior, so that we get the next possible probability value of the next toss, right? So we are not going to see the solution, but the final solution, the computation of these steps you can try out, but the solution I will write. So solving this, we get P of x, the next coin toss is x1, x1 xm is equal to, so possibility of getting a next head, right? So this is m of heads plus 1 divided by m of 1 plus m of 0 plus 2. So you just recall the MLE function that we have computed. So MLE was m of the number of heads divided by the total number of tosses, right? But here you can see additional terms are coming up. So these additional terms are basically one count with the outcomes, right? So each outcome expressed in this equation, stated in this equation, is added with 1. So m1 added with 1, m1 added with 1, m0 added with 1. So both ones here you can see that it is 2, right? So some imaginary count, right? Count was added, right? So this is equal to MLE plus some imaginary count added. So I will write it as so this is nothing but MLE plus an additional imaginary count or a value, right? Imaginary a sample to each count, right? So this is the basic difference between MLE and the Bayesian approach, right? And you can see that as number of samples increases or grows, the Bayesian estimate and MLE will converge to same value. So because as this becomes a large number, right, and this becomes a large number, so these additional counts will be very, very small, right? So this is the Bayesian estimation approach. So this particular count, the imaginary count, is referred to as so the particular estimator that corresponds to a uniform prior is known as Laplace's correction, right? So you can read more about this Laplacian correction from the material. So to summarize, we have started with Bayesian estimation approach, and we try to compare it with maximum likelihood estimate. So in maximum likelihood estimation approach, we do not have a freedom of adding prior notion into the model. So it's a single value. MLE gives you a single value. So in Bayesian approach, we can add the prior and we can update the probability values by computing the posterior. So the MLE approach gives you only the likelihood estimation, but in Bayesian approach we can add the prior and update the probability values. So this is the difference between MLE and Bayesian estimation. So I will close this lecture with this note. Thank you.